it's a pleasure to give this seminar. It would have been even better if I could travel there, but webinars are also making easier the communication with the universities. So today I'm going to talk about my recent work with Leonardo Egidi, and I'm going to guide you in a Bayesian quest for finding a unified model for predicting volleyball games. This is a joint work with Leonardo Egidi from University of Trieste, and I am currently the head of the department at the Athens University of Economics, where we have a group with a similar name as yours, Athens University of Economics and Business, AUEB, Sports Analytics Group. And we have annual meetings. Of course, now the annual meeting is a little bit delayed because of COVID. And we have also very active research community here on applying methodology, statistical methodology, mainly on sports. The last years, I'm doing more and more about volley, and this was initiated by my collaboration from my good friend Sotiris Drikos. So now we are finishing another work with him. And in this current talk, I'm going to talk about some model that it will taking into consideration both sets and points in a volleyball game. And the structure of the talk will be the following. I'm going to start with a brief introduction about the game and some initial characteristics related with modeling volleyball. The second section, I'm going to focus on the features of the game, and the features of the games here are very important. Why? Because volleyball is different than other team sports, and these unique features need to be taken into consideration in the modeling formulation. So that's why here I'm going to say the details, the unique characteristics that we need to model. And then step by step, we are going to build our model in order to satisfy and include these characteristics in our modeling procedure. Then I'm going to present some model extensions that they will lead to the unification of the model. And finally, I'm going to present some results from the Italian League and about the validation of the model. That hopefully it will be used in the future for further research. So a brief introduction. Volleyball is different than other team sports, and the literature is limited. Here I have two indicative publications, Ferrante and Fonseca, and Gabriel. Gabriel is quite close, but not exactly the same with what I'm going to present today. There are also other publications, but with more basic analysis and without considering the specialized characteristics of the game. But still, if you compare it with football, basketball, or baseball publications, then the quantitative work, the modeling work is very limited. The main reason for that is the game complexity. So in most sports, we have one level or stage of outcomes. So in basketball, we have points, and in football, we have goals that we model directly, and the winner is announced the team with the highest number of goals or points. But this does not happen in volleyball, and in general, in the whole category of net and ball games where tennis is included, and other similar games. So here in volleyball, we have two outcomes, the sets and the points are nested. They lie within each set. So let's see in detail the characteristics, the features of the game, and how we need to model it. So we have the game winner is announced when a team reaches first the three sets, and this is the winner. And the main difference here of volleyball is not only that we have these two stages, but in basketball and volleyball, hockey, or other team sports, the number of goals are counted within a given pre-specified period. Here, the winner is the one that will achieve the number of sets first. So this is an important difference. So we have a game winner when a team reaches first the three sets. It wins first the 3 sets, and then we have the set winner. It's the team that first wins 25 points. Then we have the tie break, which is again a set, but it's a special set. Is the set that is played when we have a draw between the 2 teams at 2-2. So when the 2 teams are very close, the last set that it will announce the winner, it is called the tie break. And instead of playing at 25 points, it is played in 15 points. And this was initially done in order to reduce the time played, in order to make the sport more attractive for the television. Another very important characteristic is that when we are inside a set, the winner is announced in 25 or 15 points, depending if we are in a tiebreak or not. But there is a requirement, and this requirement is that you need a difference, a margin of 2 points, in order to win, to be announced as a winner. Otherwise, the game is continuing until you have the 2 points of difference. And this can make, if you have a nice game with 2 teams very close to each other, then this can extend the game time, the game period a lot. So there is a natural hierarchy of points within sets, and we need a hierarchical or conditional approach from sets to single points in order to account, to get all the data. Of course, you can model the two things different, but the sets are the most important because they lead to the winning of the game. So maybe you have teams that in terms of points, they don't perform very well, but they are very effective at the end, while the points, they are more frequent events and they have more information. So you need to combine these 2 information in order to get a good estimate of the ability and the efficiency of the team. So now the responses here are the number of sets won by each team, or alternatively, you may even model the number of sets played in the game, and the number of sets for each team. This is from 1 to 3, so it's very the number, the range is very limited, or the number of games played again is from 3 to 5, and also the difference is from 1 to 3, and the number of points, which will go from 0 to 25 or 15, depending if we are in the tiebreak. So this whole structure is challenging from a statistical point of view because there is no distribution that it will account for all these characteristics. So we have 2 responses, and we need to set up a hierarchical likelihood or model with 2 stages, and the sets to be conditional on the points, or the points to be conditional on the sets if you do it vice versa. So you can have 2 directions of modeling here, and you have repeated measures of points within sets because you have 3 to 5 sets, and this creates a repetition of the observation of the abilities. Of course, the sequence of the sets also plays a role, and the important here is, if you think in football, for example, you have again the outcomes of 2 teams or the goals of the 2 teams, and you can assume that you need both of these outcomes in order to predict the exact score. But in volleyball, it's not something like that. Why? Because let's assume that we have the simplified scenario that the margin of 2 points is not needed. Then from the two teams, the points of the 2 teams, one of the 2 is always fixed, and this is the number of points of the winning team. The number of points of the winning team will be always equal to 25 or 15 based on which set you are, and the only random variable is it is the points. It refers to the points of the losing team. So this is very interesting because in all other sports we have 2 random variables. Here actually we have 1 because the one of the 2 we know. Not only that, we have this margin of 2 points that we need to take into consideration. And I split these 2 points because this is how we are going to model we are going to model these two characteristics a little bit separately in an accumulated way. And then we have the tie breaks that we need to adjust our distribution for the 25 and the 15 points, and this is slightly easier than combining these two characteristics. Let's come to our initial notation here, and let's denote by y alpha and y b the points in set S. So the subscript here S refers to the sets when a team A plays with a team B in the home of the first team. And then we also introduce a W, which is a binary indicator, WS, for identifying the winner of the corresponding set. So if you combine these two bullets to these two random variables, then you can specify this quantity, this random variable, and this will be equal to the number of points of the losing team, and this will range from 0 to 23 in a normal set without any extra points. So for simplification at the beginning, we will assume that the set terminates at 25 points, and then we'll add the extra component in a second step. So here, if you think, because this is binary, if we have the home team winning, then we take the points from the second team, from the away team. If we have the home team losing, then we take the losing points from the home team. And here is the two levels of this first initial model. You have the WS following a Bernoulli distribution. So this is the success. This specifies this is the success probability of the home team for set S. And this will be modeled as a simple logistic regression model. And here you have the home effect. The constant will play the home effect in terms of winning a set. So this will be the log odds of winning a set when you have teams of equal ability, and these A's here, they they measure the efficiency or the team ability for in units of log odds of winning a set. Okay, so when you have two teams of equal strength here, this will specify the home effect in terms of log odds of winning a set. And the second level will be conditional on WS also, although some people, they will consider the other way around, but the other way around is very difficult to specify the distribution. So we decided to go in the opposite way in order to be able to specify the distribution in an easier way. So here, when you know who is winning, who is the winner of the set, you know that you have a distribution here which is bounded to RS minus 2. So RS here will be 25 or 15, depending on if we are in a tie break or not. So this will be specified here. And here we use a negative binomial distribution because it's quite natural to have the winner, to have the first team that reaches the 25 or the 15, the 23 or the 13 points. So that the game terminates, the number of points that we can take is from 0 to 20 to 23. So here we take again we work with the log odds, but now the log odds will be the proportion of the probability of winning a point, and this will be again modeled with a constant term, with a home effect, and some abilities or efficiency parameters, team efficiency parameters, that it will now specify the efficiency in terms of points. And this W here controls for which team we are modeling the points. Remember that WY, that Y here is the number of teams of the number of points of the losing team, not the winning team. So this is very counterintuitive at the beginning. So when you have the home effect, the home team winning, then the home effect will disappear from here. When you have the home effect losing, then the home effect will appear here. It's the opposite. And here, this term will control the sign, the difference between the abilities. Okay, so be careful about this, which is a little bit counterintuitive. So here, again, this is the probability of winning the point for the losing team. And how we are going to deal with the problem? We are going to use the Bayesian approach, of course, because I'm Bayesian, and we are going to use non-informative priors, but easily in sports, we can find information about parameters if we want from historical data, but still building priors from historical data is another paper. And we use sum to zero constraints for the abilities. Remember, we have two sets of abilities now. We have one set for the point abilities and one set for the one set of abilities for the sets won by each team. So this can be also thought about the efficiency of the teams in the different outcomes. And then we have used JAGs within R in order to implement the MCMC and take the estimates. And we implemented all this analysis in Italian data of the season 2017, 2018 from the Italian Superlega. So this is the first initial idea, the first way to think about the model. But remember, we have the margin of 2 points, which is very important. So in the previous specification, what we did, we added here a latent component, this OS. And this OS will be the number of extra points played when we have a tie. So this OS will be modeled by a zero inflated Poisson distribution with a different parameter. And here this OS will have high probability to be zero, so not to have any extra points, and some rate to go over the 23 points. So here is the full specification for that. We have also put the abilities in the linear predictor of this success probability, and we have used also quadratic terms here, but these were not found to be significant in our approach, so I'm not going to refer to more details in this. You can have a look in the paper for the details about this, and the paper has appeared in the last issue of the Journal of the Royal Statistical Society, the Applied Statistics. And one last component is here. Remember that we have multiple measurements of the set points. So here we have also used some random effects in order to account for the correlation across sets, across different sets, of the correlation of the points across different sets. And this is the standard error of these random effects, and you will see that the mode is not at zero, of course. It's a little bit further away from zero, but the value is quite small. And this is an indication that there is some kind of dependence here, but this is not very strong. And this will be also confirmed by this table. So here we have 4 basic models that we compare. The first is the simple Poisson, which is inappropriate in the sense that no feature of the volleyball is accounted. And the second is the truncated negative binomial, again with no upper limit, so no extra points, no characteristic is accounted, and it is even worse than the Poisson. But if you go to the zero inflated Poisson, truncated and negative binomial model that we have introduced, this improves things quite a lot, and the random effects is slightly better with a model without random effects, but the difference is quite small and the number of parameters is increased a lot. So here we decided not to put it in the analysis since we don't gain too much in terms of DIC. So in principle, some people may say, okay, I want to have these random effects, but here, mainly for computational reasons, because this model is much faster than this one, we decided not to put it in the following analysis. Some model extensions. So the previous model is fine, is nice, but there is no unification. So we model together, but we get different efficiencies for sets and points. So actually, in principle, is similar, not exactly the same, but similar, like modeling two separate models for the sets and the points. But this one was not the issue of this research. We wanted to have information going from one level to another in a more immediate way. And this is why we proceeded to this extension. And here we have the abilities of the sets, the original abilities of the sets. And here we have the abilities from the points, and we have put both of them in the probability of winning a set. Here, these indicators, they are binary indicators taking values 0 and 1, and they control whether we should put this component or this component in this linear predictor. So here, if you take the combinations of these V1 and V2 indicators, we have 4 different models. So the 4 different models, the first one is the model with which the probability of winning a set is not influenced by teams, which is the constant model, is totally non-realistic, not realistic. So we do not gain much if we use this approach. The first one is the model that has here only the set abilities. So this is the model that I have already shown in the previous slides, is the model with the disconnected ability. So we have abilities for sets, abilities for points. They are not directly connected. And this model does not have this component, but it has this component. So here we have one set of abilities, and these are connected. They go in both levels with different scaling, different linear scaling. And finally, you have, if you put both of them, you have these parameters taking information by set and points, and here these parameters will be something like extra efficiency of the teams in the level of the sets. So actually here we expect some teams to be similar with this efficiency and some teams to be different. And these are the priors, non-informative priors, so flat variance. The additional here is that we have used also dynamic abilities. So the dynamic abilities are like random effects, but they change from week to week. It's an autoregressive component. It's very usual in sports, especially in football, to put components like that. So you don't have a constant ability, but you have an ability which changes. And here you can see these point abilities for each team, how they change. If you will notice, there are some variabilities, of course, but the differences are not so great. And this is the random effect here. You will see again, the standard deviation is very, very small. And this is confirmed here by this table where we compare multiple models. So the first comment is here that either the dynamic abilities in points or the dynamic abilities on sets do not improve the DIC too much. Actually, here we have a small improvement, but if you compare it with the rest of the models that I'm going to discuss, this improvement is not critical. The second is that if we put both abilities in the model, then we have a model which is slightly better. But if we put a model with connected abilities, which means both abilities going to the point and the set level, then the model is improved in terms of DIC. So this model seems to be slightly to be better, but this, in comparison with this, it created a little bit of motivated us to search why here we have a small improvement, although we have some kind of connected of putting both. This claims that there are some differences between the set and the point efficiencies of the team. So that's why we wanted to search it more. And by searching, and I'm going to show you 2 graphs in a while, we found that if there are 2 teams, Verona and Padova, which had a different efficiency in the set level. So if you included the set abilities only of these 2 teams, this improves the model. So especially if you connect it with this one, we don't have any separate abilities, then this is slightly improved. So we ended up to use this final model with Verona and Padova having extra abilities. And we can see here the error bars, the posterior error bars. Here are the point abilities and here are the set abilities. And you can see here these teams are quite at the margins not outside the posterior intervals, but quite at the margins in comparison with other teams. So we started playing with these two teams, and we ended up to this model. This is the model we ended, and this has better DIC than the previous one. Again, the zero value here is at the tails of the posterior. So some people may say, okay, we can remove it, but in terms of DIC, this makes a difference. And here is the full representation of the model. For many people, might look very scary, but this is a beauty for me. It's my child. The next slide will refer a little bit on the fitness of the model. So here we have generated leagues, and we have compared from the predictive distribution using all data. So this is like a Bayesian goodness of fit measure. And if you will see, here we have the expected points according to the regeneration, and here the actual points. You'll see the ranking is almost the same. We have very small difference here because these two teams had the same ranking, the same points, and here we found 1 point difference. So let's say that we have a small difference here. All the other points, they have difference 3 or 4 or 2 or 1 points difference of the fitted values of the expected according to the model and the actual points. So this is reproduced by the predictive distribution by using about 3,000 leagues, different leagues. And these two plots is the probability of success, again using the predictive distribution, but now we have not used the whole data, so this is out of sample prediction. The previous was in sample prediction, which means goodness of it. And here we have the mid-season proportion was about, on average, close to 80%, slightly lower, close to 70%, a little bit higher than 70% when we use the full season to predict the playoffs. Here we use the mid-season to predict the rest of the season. This is quite reasonable because here the games are of greater importance. So even teams, and they are knockout games, so the teams are giving their best to go to the next round. And here we have the expected points using all data. We have the actual points, and we have also the predicted values using the mid-season data. And we can see that only here with the mid-season data, we lose only two teams. Two teams are outside the posterior intervals. This is Padova and Trentino. And similar is the picture here. Here we have the rankings of each team. You can see in most teams we can achieve with red the actual ranking, and this is the posterior mode. There are some exceptions. For example, here this is Trentino, and here is Padova. Here the mode we estimated that with the half of the data the ranking was a little bit higher with the posterior mode, but all the others you will see that we are either in the mode or in the second best ranking, close to the true ranking of the teams. And this is the predictive the prediction for the playoffs games using the full season data. So we consider all the full season data and we reproduced the playoff prediction. And you can see here the probabilities according to the predicted distribution. You will see that all probabilities can identify the winner, while there are some difference. For example, here the prediction is quite good because the two teams were quite close. Here, Perugia was considerably higher in terms of prediction probability. 1, in principle, it's not 1, but it's very close to 1. But it is in all leagues, in all tournaments generated with this approach, we found that Perugia will be the winner. But the game was a little bit closer to 1 in terms of sets. Here the difference is high, so we predicted very well the difference of 2 sets. Here the difference is high, but nevertheless the game was more equal. And here we have the probability to be closer, but Lube went to the final. And here again, Perugia was the favorite, and Lube had the lower probability. Nevertheless, the game ended up 3-2 games. This is games, sorry. And here we have the probability of winning the tournament from the beginning up to the top. So you can see Perugia here had very high probability, 74%. Lube was the second, but by far 14%. And then we had other teams with lower probabilities, or the rest of the teams with lower probabilities. This is the more detailed table, which says what was the probability for every team to reach to every stage. For example, here, Perugia had 96 probability to go to the final, Lube 58%, Modena 28%, and all the other teams lower probability. So to conclude with, this is a new unified model. The proposed model accounts for all volleyball characteristics. It combines information from both sets and points. And I think it's one of the first that they do this. The fit is excellent for a practical problem. We have fully regeneration of the league. The out-of-sample prediction is good, especially if you think that we have not used any other information except the teams that are playing to each other. And the proposed model overall has very good predictive ability. So for future work, what are we working on is to extend the model to incorporate covariates using Bayesian variable selection. And the aim on this approach, we can have two different directions. The first is to understand which skills, as they call them in volleyball, they have the greater importance in the final outcome. And this is important for managers in order to identify the weakness of the team and how they can train their teams to improve. And the second, which is of lower importance, is to build predictive models using covariates. And I'm saying that this is a secondary importance because all the people that they bet and they are interested in prediction, they do it for football, basketball, or baseball, sports that are more popular than trying to predict volleyball games. And time for lunch for you, time for evening coffee for me. Thank you very much for being here in this seminar.